let's wait another minute or two and then get Bruno.
Mm-hmm.
Oh dear. Some people are apparently having trouble connecting, which is weird. Did any of you need the passcode to connect?
No, I
didn't think
didn't. I
you
just
didn't. That's what I thought. If you click the link that I sent, then it just
Right.
works. But I will.
I didn't either.
Yeah. Okay. So I have some folks emailing me. So I have to find the passcode. Sorry about this. Okay. I just sent it. Okay. Well, okay. We're 2 minutes past the official starting time, so I think maybe we should get started, and then some more folks will almost certainly connect momentarily. Okay, so welcome everybody to our first sort of spring semester Confinement Collaboration Seminar. Today we're very fortunate to have Bruno Scheihing Hitschfeld from MIT to start things off with a very interesting talk about Quarkonium and quark-gluon plasmas. So go for it, Bruno.
Oh, well, thank you. Thank you so much for having me. Please interrupt me at any point of the talk if you have questions. And yeah, I hope we have fun discussing about these recent developments on Quarkonium and quark-gluon plasma that I want to tell you about today. This is work done mostly in collaboration with Xiaoyun Yao and Holvert Nice. Xiaoyun is at the University of Washington. Holvert is at CERN right now. So let me just get started. Before actually making a reference to any of the words in the title, let me say what the motivation for these studies is, which mostly comes from heavy ion collisions. So which is where we can form, or where we collectively can form quark-gluon plasma in experiment and ask questions about it and study things like some questions that I figure you might be very interested in, such as confinement, deconfinement transition. Okay, so what happens in a heavy ion collision is that you have two flat pancakes due to a high Lorentz contraction of nuclei that you collide onto each other. And then after the collision, a big mess of particles starts flying around. But if you zoom in into the very early stages, just after the collision, in between, say, 1 Fermi over C after the collision and 10 Fermi over C after the collision, you'll see that there's basically a red blob in this simulation on the right here, which represents the fact that at such early stages, the matter that collided is actually in local thermal equilibrium. And there's plenty of evidence that supports that, which I'm not going to go into right now. But that's just to say that this is a physical system where you can actually study QCD at high temperature. And even more so, you can try to ask with what objects we can probe this system at high temperatures. And as it turns out...
just very basic question. How do we know it's equilibrated? Because it's expanding very fast.
You don't know. Well, it's not in global equilibrium, but locally, you can you know that it reached local thermal equilibrium because you can look at the distribution of the momentum of the particles that are coming out of this blob. So as it freezes out, and then you can essentially tabulate what the distribution is in terms of momentum, energy, mass, etc. And you can then look. And after you look at that, you'll see that all of them follow Bose-Einstein distributions or Fermi-Dirac distributions, thermal distributions, with the same temperature for different mass species. So that tells you that something had to happen in between for these particles to agree on a temperature, at least. And then you can ask questions with more details.
And the temperature you get is around where?
It's around the freeze-out temperature, 150 MeV, 160 MeV. And there's also measurements about flow that, in terms of if the initial collision was not perfectly central, then you expect some asymmetry in the final in the particle measurements you make at the end of the collision. And you have to model you have to describe how the interactions happen between the initial state to transform it into particles flowing to your detector. And it turns out that hydrodynamics does an almost perfect job at that, which again suggests that the system did reach local thermal equilibrium. So it's of course, you don't have a direct measurement in the sense that you cannot just form a blob of quark-gluon plasma in your laboratory and let it stay there for indefinite time. What you do in these systems is that you do a collision, and based on the debris of the collision, you try to decide whether the system reached local thermal equilibrium or not. And all the evidence that we see from measurements is that if the collision system was large enough, then indeed the statistics that you get out of it are completely consistent with local thermal equilibrium.
Okay, thanks a lot.
Yeah, and but then you can ask, well, you know that that it did reach local thermal equilibrium, but it doesn't tell you much about the microscopics of this fluid, if you want, of the quark-gluon plasma. For that, you want probes that can have some level of resolution of the structure of this plasma. And that's where what people call hard probes come in, such as jets, or what I'm going to be focusing on for the rest of the talks, which are heavy quarks, which they can also come as jets. But what I'm going to be focusing on in more detail is on bound states of heavy quarks, quarkonium in detail, specifically. So the idea here is that heavy quarks will be produced in the initial hard scattering, when the energy of the collision is actually sufficient to form these heavy quarks. But because their masses will be large compared to the temperature of the fluid that will be formed after the collision, which will be of the order of a couple hundred MeV and cool down to 150 MeV or so, at which point it will start to hadronize. They'll never fully thermalize. And so in that sense, they behave as external probes, and you can use them to ask questions about the quark-gluon plasma. One idea that was put forth very early on and is still around is to use the suppression of bound states in heavy ion collisions relative to proton-proton collisions as a measure of the temperature of the system, as a thermometer, if you want, because the quark-gluon plasma, in principle, will be able to screen the interaction between two heavy quarks that could bind into a bound state, and therefore you would naively expect less bound states, fewer bound states in your final state in a heavy ion collision as compared to a proton-proton collision. This I will say again later on in the talk. So I hope that point will come across more clearly once I've introduced more concepts. So, well, that was the broad motivation I wanted to give you. Now let me discuss in more detail what are the players of this game I want to play. So I want to talk about bound states of heavy quarks. These are called quarkonium. Specifically, the ones I'm going to be interested in are charmonium and bothmonium, These have been well studied in many other ways that I will not get into, but for the purposes of what I want to discuss now, let's just say that they're bound states of a heavy quark and an anti-quark with masses that are much above lambda QCD, and binding energies, that's to say splittings between their energy levels of the different states they can form, of around a couple 500 MeV or so. A bit more conceptually, if you want to write this out a bit more systematically and along the lines of eventually writing out an effective field theory for this system, you can then lay out all of the scales in this problem, starting from the masses of the heavy quarks, which in each case is, say, 1.5 or 4.5 GeV, the typical size of the bound system, which is in this case one of the order 1 GeV, the typical inverse size rather, and the binding energies, which are of the order of 500 MeV. I've here depicted as these lines and these segments, horizontal segments in my slide, the associated length scale to each one of these numbers for the bottom quark, for the case of bottom quark and bothomonium. And the fact that you have this hierarchy of scales makes it even more interesting, and because of the heavy ion collision motivation I gave you earlier, even pressing, to study this in a thermal environment. And specifically when the thermal environment has a temperature of around a couple 100 MeV. So for definiteness, I here just have shown what the equivalent length scale is to 200 MeV. And if you then start zooming out from this picture, and you look and you go to a reference frame if you want, or to a frame in which you can see the size of the system you collided, which is around 5 Fermi in width. That's the radii of the atomic nuclei of gold or lead that people collide at the LHC or RIC. Then you'll see that the temperature is still a scale that you can distinguish by eye, and it's pretty much something important here. But the size of the system of a quarkonium bound state here is comparatively very small. So for most purposes, in terms of its dynamics, it might be useful, which is what we will do in what follows, to treat it as essentially a point particle. And each of the bottom quarks themselves is clearly a point particle given because of this very small distance that's down here. And so this is all to say that we're going to exploit this hierarchy of scales to study the system inside the quark-gluon plasma. Now, I've only introduced you to the kinematics, if you want, of the system, but we also have to specify dynamics. How are these two things coupled? How do they talk to each other? How can the quark-gluon plasma interact with this quarkonium bound system and make it evolve non-trivially, and so that we can actually see a difference between it being in vacuum or at finite temperature in terms of the environment that is the background to all of this. And well, in the limit where this system is very tightly bound, or rather that this typical distance between the heavy quarks is small compared to all the other distance scales in the system, you can essentially treat the interaction of the heavy quark pair with a medium by doing a multiple expansion of the interaction with a gauge field. And the first term that appears here is an interaction that mediates a transition from an octet field to a singlet. Here, O and S are second quantized creation and annihilation operators of non-relativistic heavy quark pairs either in the octet state or in the singlet state. And in the sense that you're looking at that as a subsystem where you've traced out all of the environment degrees of freedom and want to ask questions about whether the quarks are bound together in color or not. And the operator that mediates this is a chromoelectric field, and it is suppressed in terms of the power counting by the typical distance that separates them. This, if this is conceptually, if it seems different to what one would usually do in quantum field theory, well, fear not. This is very much something that you would do even in quantum mechanics when you study transitions between energy levels of hydrogen. You want to understand how often or how an electron can jump between one state orbiting around the proton to another state orbiting around the proton, and that will be mediated by interacting with light of a definite frequency that will scatter off it. It's the same concept here. The main difference, the crucial difference actually, is that because the particles that can mediate this transition are also color charged, it's not just a jump between energy levels, it's also a jump between whether the system is bound in color with itself, or whether the color connections have to go to the environment. And well, phenomenologically, if you want to actually go back to the motivation I showed you in the first couple of slides, these interactions can both recombine and dissociate quarkonia as they propagate through the quark-gluon plasma. So if you want to set things up in a model for heavy ion collisions to describe and calculate what are the abundances of bound states you expect at the end of the day, you need to take this into account. You need to know how much the quark-gluon plasma regenerated and dissociated the potential bound states of heavy quarks, which will be produced in the initial hard scattering, and then will evolve dynamically, assuming they're close to, and they're sufficiently close that they can actually interact non-trivially. So, well, that's the broad picture I want to sell here. If we want to go into a bit more detail of what is the Lagrangian I'm using and what specifically how you set up each part of this system, I have this slide here for you, which tells you that the universe, if you want, that I'm going to be considering is made up of three building blocks. One of which, and I'm going to be thinking of this very much as an open quantum system in the back of my mind. I'll not be making too many references to it, but that is what I'll have in the back of my mind. One of the main building block, the main ingredient that we need here is actually the system whose degrees of freedom we care about, which is the Quarkonium pair, the heavy quark pair system, which can bind into quarkonium, which is characterized by a set of energy levels that can be formed, that quarkonium can bind in, and it can also unbind. And this part will be described here by single particle Hamiltonians. I'm going to be assuming that the dynamics, or rather the physics that makes the formation of these bound states possible, and actually what these states are going to be given to me by some other calculation that I'm not going to pursue here. I'm here going to mostly be pursuing the question of how these different states that you could calculate in principle, how does the dynamics with an environment induce transitions between these states and alter the final abundances of them. Then the interaction that will mediate which will be implementing precisely these transitions will be an exchange through this dipole type interaction that I introduced in the previous slides, which is encoded here in the terms that are underlined here by these orange lines. Also, because the octet, or rather the unbound quarkonium, will be color charged in the adjoint representation, there will be some interactions through the covariant derivative here. And finally, their environment, quark-gluon plasma, will be described by the light QCD degrees of freedom. And the only scale for current purposes will take to be the temperature, which is essentially around the same scale as lambda QCD for our present purposes. So it's just this for all we care about at this point. And then once you have all of this set up, you need to ask, well, what object can I formulate in quantum field theory, to describe, characterize the dissociation and regeneration rates of quarkonium in medium. So if you have a heavy quark pair that's either in a singlet or in an octet, or in the adjoint representation rather, how often will it transition to the other representation or to a different state, and what do you need to calculate for that? The answer to that question is given by what we call generalized gluon distributions. And there's one for dissociation and one for recombination. I'll introduce them in detail in the next slide, next few slides rather. But for now, you can just think in the weakly coupled limit, you can think of them as the collection of these Feynman diagrams that represent the transition between, say, a singlet and an octet state, where there's a scattering with, say, a gluon from the medium, or either with a light force from the medium with a gluon that carries the force in between. And you also have to consider higher order interactions. And eventually, because the medium in a realistic heavy ion collision is actually strongly coupled, because QCD is strongly coupled at those scales, this is not enough, and you want to define objects that can be written down non-perturbatively in the coupling constant so that you can actually make predictions of what the dissociation and recombination rates are. With that being said, let me just tell you what the answer is. The answer to these to the question that says, what objects do I need to calculate if I want to describe the dissociation and recombination rates of quarkonium and medium, is given by these chromoelectric field correlators stressed by adjoint Wilson lines in a stapled shape. And I find it easier to explain why these operators, by representing the physical process at hand at the same time. So if we look at the one on the left here, which represents dissociation, there is no operator insertions before the time t1 here, which is representing the fact that at early times this correlation function is representing a bound state in a color singlet. So there's at leading order in the EFT, at zeroth order rather, there are no interactions that happen here. And it's just a bound state that's flying around and staying there, evolving in time on its own. But then at some point, this small interaction that's controlled by the size of this bound state will kick in and will make it transition from the singlet to an octet state. And after it's an octet, then now it's color charged. So you have to take that into account. And because it can now interact with the medium through these soft gluons, emissions or absorptions, you have to resum these into a Wilson line, which ultimately gives you the Wilson lines that you get in the correlation function. And then you can ask, why do I have two electric fields instead of one that I've shown in the depiction on the right here? The reason is because you actually want a probability, a rate of the occurrence of this process on the right. And this process on the right is essentially the amplitude for this to happen. So you do what you usually do, you take the absolute value squared, which then in turn gives you two copies of this and gives you this chromoelectric field correlation function with an adjoint line connecting them. Same thing for combination. Yes.
Just a question in the previous picture. So what about quark pair creation? Before forming a Wilson loop, a long Wilson loop, I would have thought that it could, the string could snap pretty easily, and you just make two heavy light mesons.
Oh, you mean this string between the?
Yeah.
Well, in some sense, that is what is happening. I mean, the global state of the system will still be a singlet. So what I'm saying here is that this is the correlation function that you need to keep track of after you trace out the environment degrees of freedom. After you say that the question I want to ask is whether the heavy quarks are bound to each other or to something else in the medium. And in that sense, when you transition from a singlet to an octet here, to say that perhaps in a more formal way, Gauss' law will still be satisfied. It's just that the things that you have to take into account for Gauss' law to be satisfied will now be in the environment, so that you still need you still need this color. The string, if you want, that connects these two heavy quarks will still be connected, but to something else in the environment. And I'm tracing that out. So what you'll see here in terms of an operator will just be a Wilson line, which actually in the holographic setup I'm going to discuss later will be pretty plainly be a string hanging down into the environment, saying that this piece of deconfined matter is actually has to be coupled to has to be bound to something else in the plasma.
Mm-hmm. I guess the thing that I'm very naively stuck on is I would have thought that what the decay would look like is, two quark here, anti-quark here connected by a Wilson line. You could think of that being as an interpolating operator for a bound state, and the thing that would decay to are two extra. You'd pair produce some fundamental quarks, fundamental, anti-fundamental, and that would be the overlap. But that's somehow not totally obvious from these pictures.
Oh, it's not, because in this picture, what I'm doing is I'm saying this correlator is what you get to if you want to describe the dynamics of this subsystem where you only follow the degrees of freedom of the heavy quarks. And all of the light quarks you want to pair create or just be there in the thermal medium, they will be in the degrees of freedom I will not be following throughout this picture.
I see.
So those processes will actually be encoded here in the latter part here, where you have what I call an unbound state, which is essentially stating that just the heavy quarks are not bound to each other in terms of color lines.
I see. Thank you very much. That's clear.
So in the holographic setup, you'll have a string going to the horizon, right? Just a long string.
I'm gonna discuss that later on. So I'd rather answer that question when I get to it.
Sounds good. Sounds good.
Can I ask quickly another question right now?
Sure.
So time there is Minkowski time. Is it possible to do a weak rotation?
I'm gonna get to that as well.
Okay.
I'm gonna mention to what extent you can formulate a correlation function in Euclidean space-time. Well, that you would be able to calculate using lattice QCD techniques, and relate that correlation function that you can formulate there to these correlation functions that I'm showing you here right now on Minkowski time. But it's less, as I hope will be clear later on, it's not a straightforward Wick rotation, because in here there's also operator ordering subtleties, or not really. They're not subtleties. They're encoding the physical process actually, but there are aspects of operator ordering that you need to keep track of, and when you do the analytic continuation from imaginary to real time, you have to be careful about that. And I hope I'll be able to convey that later on.
Okay, thanks.
Okay. So next thing, well, this is for recombination, same picture. You start with an unbound state, so you'll have Wilson lines going into the past, and then at some point you're going to insert this operator from the effective field theory that you get by multiple expanding the interaction of this heavy quark pair with the environment. And then after that, it becomes a bound state in terms of color, so it does not interact further at 0th order in the EFT, and then that's all you need. And yeah, that's the correlation function that you'd write for this process. In practice, you'll notice that I wrote these out with a spatial separation as well. In practice, and that's the more general thing you can write. In practice, you need less than that, because if you want inclusive rates of formation and dissociation, You just need to calculate what these correlation functions when the spatial position of these electric fields is the same. So you need either the first one here, which is the one for dissociation, where you just have an electric field, or you have a Wilson line connecting the electric fields only in between these two, the field insertions. But the other one for regeneration, where while it still is a correlation function of electric fields connected via an adjoint Wilson line, there's the operator ordering is different, and in the end it reflects the fact that the initial state was an unbound pair where you had a heavy quark pair that was not bound in color to each other. And that means that you need to keep track of an adjoint Wilson line from the very beginning, and you cannot just remove it. It's what it is. And well, before moving on to how you calculate them and what their properties are, let me first make a brief mention to how would people right away use them in terms of transport equations phenomenologically in the quark-gluon plasma. And what people have done, which is a lot, I have to say, is to study this system in different limits. One limit that has been very well studied is the one that's called the quantum Brownian motion limit, where you assume that the temperature is still small compared to the inverse size of the system, but comparatively large compared to the binding energies of to the energy splittings between the Quarkonium states. This in real life is not going to be realized. It's because the binding energies are for order 500 MeV and the temperature is about a couple hundred MeV, 300-400 at best at the early stages of the collision. But it's still something that conceptually is useful to understand, to know, just to have some sense of what the dynamics looks like. And what it describes is the evolution of the subsystem density matrix containing as its entries the occupancies of each state and each energy level, or in both singlet or octet states, and it will follow a Lindblad type equation with free propagation and jumps between the different energy levels. And these jumps, the operator that mediates them, are proportional to the zero frequency limit, rather, of the correlation functions I introduced in the previous slide. So if you calculate what I just showed you, you can then just ask for the zero frequency limit, put it on this equation, and see what you get. In the same way, not in the same way, but in the same spirit, you can also try to go down to lower temperatures and remove this restriction where you require the temperature to be larger than the binding energy. But if you do that and you want to write a transport equation that's simple enough, what people have come up with is to write a Boltzmann equation, essentially, to do a semi-classical approximation of the dynamics, where you drop the off-diagonal elements of the density matrix and you just follow the occupancies of each state. And if you do that, you can write an evolution equation for the occupancy, say, of bound states in terms of a dissociation and a formation rate. And these rates are exactly given in terms of the correlation functions that I introduced before. The only other ingredient you need is the overlap between the states that you'll be transitioning from and into, which are also governed by the typical distance in these states. But once you have these correlators and once you have the information of what the bound states or the unbound states actually are, you can then go and calculate what this dissociation and formation rates and make comparisons with data in principle. You need to do much more on the heavy ion modeling side to actually connect this to observables. But as far as the dynamics of quarkonium inside the quark-gluon plasma goes, this is what you need to do. Okay, then let me go back to a more formal territory. I want to briefly comment on on one property that's very peculiar of these generalized gluon distributions, or at least that it was very peculiar for us when we first ran into it. And it's the fact that, well, imagine that you had a quark gluon plasma sitting there for infinite time, and you threw in a couple of heavy quarks. This will not be realized in practice, but if the system was able to stay there for infinite time, you eventually expect that whatever degrees of freedom can thermalize, say the distribution of occupancies of the energy levels of quarkonium, will thermalize. And that should be encoded into these correlation functions, because they should be able to, the system should be able to attain detailed balance. And indeed, you can prove that the correlation function for dissociation and recombination satisfy a Kubo-Martin-Schwinger relation that guarantees this. And then once you have that, you can say, well, then I don't need to calculate both of them. If I know one of them, I know the other. You can prove this formally. You don't have to actually do any calculation for it. And then you can just encode all of the information in terms of a single object, which one usually calls a spectral function. Spectral function in the very same sense that all other spectral functions that we can define, say, in thermal field theory, where it's a difference between two Weidmann correlation functions, if you're familiar with that terminology. And the curious fact about this spectral function is because you need both correlation functions to have a time reversal invariance in your system, then the spectral function associated to these correlators, defined as I introduced it in the previous slide, will not be odd under frequency. And that's simply because that's just a statement that you have different initial states in each case. And so you don't have this symmetry. And you can formally write out a spectral decomposition for it and see very explicitly why the fact that having a point charge sitting there, a point color charge sitting there in the medium versus not having one will break this property of oddness under frequency. And this might seem like a bit of a technical side point, but this is a technical side point until you actually do the calculation and realize that this technical side point is very much present in the result. And it's and the way things usually happen is actually the reverse, which is what happened to us. We first set out to do the calculation of this object, and the most naive thing you could do, you just write out all the Feynman diagrams up to next leading order in a weak coupling expansion, and in G and the gauge theory coupling, and then get a result. And then after you get a result, you find yourself puzzled at the fact that the spectral function that you naively have expected be odd under frequency has an additional term here that breaks this parity. And then you want to understand why, what went wrong or what went right. In hindsight, I just told you the answer, what went right in this case. But for the historical record, I want to show you that there had been, of course, this was not the first calculation of correlation functions of electric fields in a thermal environment dressed by Wilson lines. These have been done for quite a while, and in particular, there's one that characterizes heavy quark diffusion, from which you can extract the heavy quark diffusion coefficient in a thermal medium, which had been done like 10, 13 years ago by now. And if you compare term by term the results, you'll find that the only difference is in these pi square terms that are here proportional to pi squared, and even more so, the only difference is in the terms that breaks the parity of the spectral function. So we really wanted to understand why and what's really different between having mathematically between having a single open heavy quark sitting there in a plasma, rather than having these transitions between singlet and octet states. From a conceptual point of view, they're clearly different, but if you just started writing out the results, you might even be tempted to use the heavy quark diffusion results for to describe the Quarkonium transition rates between singlet and octet states, which is something I'll advocate at the end that you should not do. But nonetheless, it's good to have to know why, basically. And I'm going to compare a bit, just briefly, with what happens with heavy quark diffusion. What's the correlation function that you need to calculate in that case? What physics is encoded there, and then what the differences are with quarkonium transport. For heavy quark diffusion, you don't have transitions between different states of the quark, other than it receiving some momentum kick from the medium. So you just start with a heavy quark sitting there in the quark-gluon plasma. It's color charged, so you have to resum all of these interactions in a Wilson line. And then at some point, if you do this, and say in heavy quark effective theory, you can get a stronger kick from the medium that encoded in an electric field insertion, where actual momentum transfer is affected. And then for the rest of time, it'll just fly away. And still, you have to take into account that because this heavy quark is color charged, you have a Wilson line there. But other than that, you have this amplitude if you want, and if you want to calculate what's the typical transverse momentum square that you get out of this process, you'd calculate this correlation function here on the left, and it represents exactly that. It's basically the expectation value of E squared, but with addressing of Wilson lines that encodes the physical process that you're interested in. And then you can go and look at the Feynman diagrams at weak coupling and ask, well, where does this difference happen? Where does it appear? And it appears in a very clean way, in the sense that it only appears in these type of diagrams where you have both an interaction with gluons and gluons that are coupled to the Wilson lines, that essentially are feeling the fact that you have a point color charge there. And the fact that on the left here for quarkonium, you can only insert gluons at times after the transition to an octet took place, compared to the one on the right here, where you can insert gluons at the Wilson lines at any times, makes a difference. And you can just do the calculation, which is surprisingly short if you're compared to all the other calculations in terms of Feynman diagrams that you have to do to get the results that I showed you earlier. And the difference is, well, it can be stated in many ways, but the simplest way to state it here is that it is due to different operator orderings that encode different physics. In which sense? In the sense that if you actually pull these two positions of the spatial positions of the electric fields together, there are some cases in which you can rewrite the fundamental Wilson lines as adjoint Wilson lines, because they're at the same position. But you can only do that if the operator ordering is consistent with that. And here on the right, you have an obstruction to that, which is given by the initial state that you have that you need to have this point color charge present at all times. Well, this is all to say that the quantum, whatever the color state of your system is important. And well, you can even check that this difference is gauge invariant explicitly. There's I should not even say this, but in practice is something that you want to check when you do a perturbative calculation, and you can check it. And then the next thing is, well, this is a perturbative difference. How do you encode this if you want to formulate this non-perturbatively? What goes different? And well, I'll repeat many things that I said just now, but it's always helpful to see the same problem in different ways to really understand what the difference is. And for this, I want to introduce the Schringer-Keldysh contour. So for those of you who know what that is, might be everybody, but there also might be people who are not familiar with the Schringer-Keldysh contour, so I'll discuss it anyways. And the difference is that on the left here, for the quarkonium case, you have two electric field insertions, and the adjoint Wilson line connecting them goes only over one branch of the Schringer-Keldysh contour, which I'll define and introduce in the next few slides. And the other case, for heavy quark diffusion, you have a fundamental Wilson line that wraps around the whole contour. And essentially, you have a winding number that gives you a global difference between these two objects. Okay, now to give meaning to this, let me just briefly remind or introduce or discuss what the Schwinger-Keldysh contour is. It's just a path integral method to calculate thermal correlation functions in thermal equilibrium, or more generally, but for what I care about in this presentation, it will be thermal equilibrium. So the most simple one you can consider is just expectation values of operators in thermal equilibrium, where you just insert some operator in your path integral and then evolve it and then have some displacement along imaginary time representing the thermal density matrix. And from that, you get the expectation value you want. You can also calculate 2-point functions in Euclidean space-time by inserting another operator further down the imaginary time. But if you want to do real-time calculations, you're ultimately forced to deform this contour into the real-time axis, insert an operator wherever you want to insert it, at whatever temporal separation you want to insert it, and then come back and close the contour and go down the imaginary time direction to actually encode the fact that you have a thermal density matrix here. And of course, you have to impose periodic boundary conditions at the ends of this contour because you have a trace here. Okay, then that should explain what these pictures mean here. And once I've done that, I can repeat what I've said earlier, which is the fact that on the right here, you have a heavy quark present at all times. So in some sense, it's part of the construction of the thermal state of the quark-gluon plasma at the beginning, and that's encoded in the Wilson line that essentially enforces the Gauss law constraint that you have a point charge present at the initial state, and it will be there for all times. That is not the case in for the Quarkonium correlator, where you just are studying transitions from having no point color charge to having one and then back to having none whatsoever. And so this global difference is what gives you a non-perturbative difference, and you can encode it in terms of operator ordering or in terms of path integral methods as winding numbers around the Schwinger-Keldysh contour. Either way, the difference is very much there. And so now let me come back to what you would do in imaginary time. And I realize I'm going a bit more slowly than I should be going, but there have been questions along the presentation, so I hope it's good. I hope it's still good if I go into a bit over into the question time. So out of the two correlation functions I showed you just now, the one for heavy quark diffusion has been very thoroughly, I would say, studied using lattice QCD methods. One way to do that is to calculate this chromoelectric field correlation function inserted, or the electric fields are inserted along the Polyakov loop in the imaginary time direction. And then if you assume some further information about the spectral function you want to reconstruct, you can use the information from this correlation function that you can calculate to actually infer some more information about it. This problem is famously ill-posed, but nonetheless, that doesn't stop us from using it, provided that we know more information about the spectral function. And well, you can extract transfer coefficients after the fact by taking the low frequency limit. It has been much less so studied, at least from what I have seen, this correlation function in thermal equilibrium. It has been studied I am aware it has been studied if in vacuum, but in thermal equilibrium in the background, I'm not aware of lattice studies that have had a focus on this, aiming at quarkonium dynamics. So we decided to work out what you would need to extract from here to get the spectral function that I introduced earlier. And as it turns out, it's not that much more complicated. But in terms of some of the formulas that you'd use to invert the extraction of the Euclidean correlator to get the spectral function, some other aspects of the analytic continuation get more complicated. And for that, I'll have to refer you to our paper earlier on last year. But you can still extract transport coefficients from the spectral function here. And the complications are either due to different analyticity properties or to the fact that this correlation function is explicitly now, it's not invariant under reflections, if you want, along imaginary time, because you have a Wilson line distinguishing one segment between the electric fields with the other way of connecting them across the other side of the periodic Euclidean time direction. So that's as far as we got in terms of formulating this in Euclidean time. So in the last 5 minutes, and I hope I'll have 5 minutes for this, I want to show you briefly, because what other evidence do we have that these how should, in absence of a lattice QCD calculation, what prior do we have on how these objects look, on how, especially the one for Quarkonium that has not been that has not received too much attention. And so we did an n=4 super Yang-Mills calculation using the holographic duality of this spectral function. And we found the difference to be dramatic in the sense that numerically, even though the ingredients that go into the calculation can be much the same, the actual spectral function, apart from their large omega behavior at positive frequency, they do not agree at all. And so let me briefly mention what goes into this calculation and how this happens. What we do to calculate this is to use the old result by Maldacena that one can evaluate expectation values of Wilson loops by extremizing a classical string action hanging from the contour on the boundary on which the Wilson loop is defined. And then once you have an expectation value of a Wilson loop, you can do small deformations on the path that the Wilson loop is defined on, and that will generate field strength insertions, which is in essence the same thing that one does when you formulate the lattice regulated version of a chromoelectric field correlator. You take the Polyakov loop, and then you take two different ways of going around plaquettes to calculate this correlation function. I heard something. Was there a question? Okay, never mind then. And so all you have to do is specify what the metric on the holographic dual side, on the gravity side of the description is, that corresponds to a thermal background. This is an ADS Schwarzschild black hole, and you can go ahead and do the calculation, whose technical details I'll spare you from. But in practice, the essence of the calculation is that you have to find an undeformed Wilson loop where you'll insert small deformations encoding field strengths. And then on the gravity side, what that means is that you have to study how small deformations propagate into the bulk, how these modify the value of the action, and then take derivatives with respect to that, which will ultimately encode the expectation value we're after. Very schematically, what we found that you have to do, and what matters most to account for this difference, is the fact that because in the Quarkonium correlator, the electric field insertions are only on one side of the contour on the time ordered branch for definiteness. The extremal surface, this is a schematic picture, has not anything to do with it doesn't have much to do. It has something to do with a precise quantitative solution. But it will be closed only within that time branch, that branch of the contour. And this is something that we followed the discussion by Skenderis and Van Drees about 15 years ago of how you'd implement the Schwinger-Keldysh contour in holography. And if you do that for the heavy quark case, because you have to represent all this Wilson loop as a path integral with non-trivial operator ordering, you'll have now here a heavy quark present at all points. So you'll have a surface hanging down through all patches of the bulk that are dual to them, to the boundary segments that encode the Schwinger-Keldysh contour. And you have to propagate fluctuations throughout all of it, and you have to impose those periodic boundary conditions on the string, which gives you the usual KMS relations that you would expect. And they do not come out naturally in the other case, because in that other case, the surface is entirely contained within the time-ordered branch. And from here, you get the heavy quark diffusion coefficient. So that's how you get this result. And for details, I'm afraid I'll have to refer you to the paper where we discussed this at length. You can also find the velocity dependence of how this correlation function depends on the relative velocity of the medium on the background. So say you had a heavy quark at rest, but the medium was flying in some direction with some velocity. And the result is consistent with what people have previously found for heavy quark probes on a medium at local thermal equilibrium, but in motion with respect to the heavy quark rest frame, which is to rescale the temperature by the square root of the Lorentz boost factor. And okay, finally, just to wrap up, what does this imply for the dynamics? If you briefly, in a nutshell, if you just use these results in the transferred formalisms that have been developed thus far, which I have to say have mostly had a weakly coupled perspective in mind when they formulated the approaches, but because they're especially the optical limit, which relies on semi-classical approximations where you can treat things as particles. It turns out that the result vanishes, and it seems to give trivial dynamics for the transition rates, which is something we wanted to be sure that it made sense. And then here there is a reminder of why that the results we got would actually imply that these rates vanish. In the interest of time, I'll ask you to trust me that that is the case, and I'll not discuss in detail why these forms of the expressions imply that the rates vanish. But it is the case. Then you can ask, well, did the result make sense physically to begin with? Compared to the weakly coupled QCD result, you can compare the trends, what happens to the weakly coupled result as you dial up the coupling from zero. And while of course you cannot extrapolate from zero coupling to infinite coupling as the holographic calculation does, the trend seems to go in that direction. After appropriately rescaling everything such that you're actually comparing things that you can compare to each other. That includes to arbitrarily rescale the plots on the right here so that the asymptotic behavior at large frequency matches, so that all the curves can be seen at the same time. Otherwise, the fact that the coupling is different will just separate wildly all the curves. So qualitatively, it does seem to approach the shape of the strongly coupled result. So it's important to have at least a prior of what to expect if it turns out that the lattice QCD calculation of these objects is closer to the holographic result than to the weakly coupled result qualitatively. And indeed, that even though the transport formalisms I showed you would predict a vanishing result, this doesn't mean that nothing happens at all. It means that we have to improve the phenomenological transport formalisms that people have been using. Because if you just go back to open quantum systems basics and you evolve the density matrix with a general time evolution operator and take up to some time, take the trace out and do time-dependent perturbation theory, you get an answer which is non-zero for, say, an octet to bound state transition, which is encoded in this formula down here. And you can actually plot it as a function of the initial condition, the initial separation between the heavy quarks. So in this case, we're calculating the regeneration probability of an epsilon-1s state starting from an octet state evolved through 10 Fermi of the lifetime of a quark-gluon plasma with a temperature profile that resembles what you'd expect in a heavy ion collision, freezing it out at 155 MeV. And then we find that there's a peak right around the separation that's characteristic of the epsilon-1s state. And then you also have contributions from resonances from the 2s and 3s state and so forth. So in the interest of time, I just want to say that that we're still in the process of actually using this formalism or these results to compare with data. We want to do a systematic scan of various initial conditions and abundances at the final stage of a heavy ion collision, because we now have some more insight into the microscopic physics that governs what the final abundances should be. There's interesting prospects to interpolate between weak and strong coupling, and we can hopefully try to understand a bit better what the non-perturbative physics of the quark-gluon plasma is. And there's also interesting challenges regarding just transport equations in open quantum systems when you need to go beyond the paradigm of Markovian dynamics, where the evolution will only depends on the state of your system at the same time. So I think I'm right on time of the question time. So I'll have to thank you for all the questions throughout the talk, and maybe ask for 1 or 2 more questions. Thank you so much.
Thank you, Bruno, for a very interesting talk. I do know we had a few questions during the talk, but I think we have some time for more questions if folks want to ask.
Yeah, just one comment about the ADS Quarkonium spectrum in ADS-CFT. I don't know if you've seen the paper that I wrote with Maldacena and Thorne back in 2006.
Yes, I did the dynamics of flux tubes, the one in 2006.
Yeah, we basically pointed out that there is a very dense spectrum right below threshold. Like if you study fluctuations of the string.
Yes, and I'm actually sorry that I didn't have time to go into it with more detail, but yeah, I'm actually not calculating that same Wilson loop that you were calculating there, where you actually.
Yeah, we were just pointing out that somehow if you just look at the string that's pinned at the boundary, right, and goes into the bulk, and it starts fluctuating a lot. Unlike at weak coupling, there seems to be lots and lots of below threshold states.
Okay.
And I was wondering how this might have imprint on the physics at strong coupling. I mean, some of the words were very similar, like we also talked about singlet versus octet. Like the octet is when the strings just separate into 2 semi-infinite strings. And
yes. So I'm afraid I'd like, well, I'm not afraid, I'm happy. I'd like to discuss this with you further at length. For now, I don't have much to say about how the spectrum of states appears in this calculation. I can say one more thing about what we're doing in this calculation, which is, let's see if I have an extra slide for that, which is that, oh yeah, at the end of the day. So because essentially we want a proxy for because this is, to begin with, we're doing the calculation in a different theory. We're doing it in n equals 4 Young-Mills, and the first object we calculated was in terms of the Wilson loop that essentially has some degree of supersymmetry encoded in it, where you have all the extra scalars. So there are some qualitative differences in the basic setup on both theories if you start from here. And then there's a choice in some sense. It's not strictly a choice, but then you can wonder what you should do with n hat here, with the S5 parameter, as you circle around the Wilson loop. You circle around the Wilson loop. And well, if you had a single heavy quark, then you just set it to a constant, because that's what would give you a minimal action. But here, we thought about it for a while, and we really wanted to preserve the property that you can form an adjoint Wilson line by a combination of 2 fundamental Wilson lines that are time-ordered. And these fundamental Wilson lines, in the QCD case, they're inverses of each other. So I want to preserve that property here. And to preserve that property, I'm demanding that the position of the S5 coordinate on either side of the loop will be antipodal.
I see.
Just because I can write the loop out in real time, and And if I write them in antipodal positions, these will cancel out exactly, and I have the property I want to be physically present there. And this is something that I'd very much like to discuss at length. But if you start from here, then you no longer are in the situation where you get the apotential between the two lines.
Yeah, that's certainly different from what we did. I think we were sitting at the same point.
Yes, right. And I mean, we also tried to make a connection with the Neumann prescription for the pure gauge Wilson loop, and along the same lines, essentially, because this choosing antipodal n hats essentially saturates the value that the Wilson loop can take, because it'll just be one. Then we argued that that there will be contributions to this path integral over that essentially enforce Neumann boundary conditions on the worldsheet, if you'd write it in terms of strings, that should lead you back to the same condition that we chose. We did not verify this explicitly because that would mean to actually having to do a calculation where you actually have a turnaround of the loop, when we decided that that was beyond the scope of what we needed to do when we did the calculation. But there's certainly some things that conceptually that are interesting that I'd like to understand better. But this is what we thought about last time we thought about it.
All right, thank you. Thank you.
Yeah. Any further questions? Go back to the conclusion.
Oh, looks like Marco has his hand up. Marco, you just jump in.
Yes, can you say something more about this thing that you mentioned right here at the end about the possible role of memory effects in the Quark plasma for this quantity?
Oh, well, I said it I said it very loosely and very generally because I confess I still have to explore what I mean by memory effects here. What I want here quite generally is to justify in this formula that I wrote here in this slide is why you cannot use why can't you write this equation as a differential equation that's local in time? What is the physics that essentially tells you that you have to keep track of the point in time in the past at which the heavy quark pair transition between a singlet and an octet state to evaluate the likelihood of that transition to happen again, and that is exactly what this correlation function here tells you. It's a correlation function in time, which tells you how the two electric field insertions that mediate the transition are correlated. And usually what people have done is to justify at some points or assume at other points that this can be written as an evolution equation that's local in time with in terms of time derivatives of the density matrix. And that would mean that you don't actually have memory effects, right? You only have the state of the system at some point in time, and that's all you need to know to evolve it one further step. That's where in the quantum Brownian motion limit, it comes out that you only need low frequency, the low frequency limit of these correlators, which you can call transport coefficients. But if you want to go away from that and keep all of the information about the quantum coherences in the density matrix, you really want finite time effects, because you want the temperature to be on the same scale as the energy splittings between the energy levels. So you want the convolution between these time evolution operators and the typical scale here in the correlator, which will be the temperature, to be commensurate for that to give you a contribution. And whether the dominant contributions that come out of that are ones that you can approximate by dynamics that are local in time or not is an open question that we want to figure out. We want to understand why. What aspects of this correlation function, beyond just saying, well, there's some things that vanish. What would you need to characterize to say these dynamics definitely come from strong correlations of the quark-gluon plasma, or from just random local kicks that give you that give you decorrelated dynamics independent of each point in time. So I fear I can only answer the question to the extent that I know what question I want to answer, but I don't have a full answer to that question yet.
Okay, thanks.
Thank you, Bruno.
Thank you
Okay,
so much.
I think maybe it would be good to wrap up. So I'm going to stop recording.